I'm going to go over something called the binomial theorem now. Now, some of you may have seen the binomial theorem. Hopefully you saw it in maybe intermediate algebra, but my guess is that many of you didn't see it, or if you did see it, you don't quite remember it. Now, the binomial theorem actually is in chapter 12 in our book, which means at the very end. And I'm not really sure why they put it so far near the end. Because you don't really need a whole lot of, it's like not like you need trig or vectors or anything to understand it or use it. And it's so useful that I don't know why it wouldn't be put in the algebra review. So I'm going to cover it now. I decided to place it in this algebra review. So even though it's out of order, this is a good place to go over it. So what does the binomial theorem tell us? Basically, the binomial theorem is like a generalization of the perfect square trinomial formula. If you remember, first plus last all squared, you can't just say that's first squared plus last squared. It's first squared plus twice first last plus last squared. And what the binomial theorem says is, well, what if I wanted to raise that to the third power or the fourth or any other higher positive integer power? How would I go about doing that? Now, one way you could do it, of course, you could always just multiply things out for a long time, but that's really inefficient. So what we want is a kind of formula that's going to allow us to write this out whenever we want to in a nice way, but also, as you'll see when we develop the formula, it really gives some insight. There's really rich meaning in the formula as well. It has applications to a lot of different things, including counting, combinatorics, which is a study of counting, and probability theory, so when you're calculating the probability of different events, and many different other areas. So it's a super important topic. It's not just about, expanding binomials. There's a lot more to it than that. So, but that's the main avenue that we're going to introduce ourselves to it. So let me start with an introduction. I'll go over just kind of the problem that we're trying to look at here, and then what I'm going to do is, instead of just giving you the formula, a lot of teachers would just give you, here's the formula for the binomial theorem, and you kind of memorize it and you can calculate it, but you really have no idea what it means, or you don't really have an intuitive feel for why it is the way it is. So that's what I want to try and do. I'm going to go a little bit past the basics and go through some things that may seem unrelated at the beginning. But then when we get to the binomial theorem, we'll be able to put it into context, and you will see why the formula is the way it is. And hopefully it'll be easier to remember, because if you understand what it's saying and where it comes from, it's much easier. This is true with anything in math. If you understand where things come from, the motivation behind them, the problem-solving process that went into solving them, it's much easier to remember everything, keep it straight in your mind, than just rote memorization. Rote memorization is not the way to do well in math. If that's what you're relying on, you're only going to get so far. You might get a little bit in math, but you're going to run into some real hurdles along the way. So I'm going to try and go through this background behind what the binomial theorem says. Okay, so the binomial theorem starts with the observation that if we square a binomial, so if we take x plus y and we square it, this is not x squared plus y squared. This is x squared plus 2xy plus y squared. So this comes from foiling, first, outer, inner, last. And then it says, okay, what if we wanted to raise this to the third power? We know we can't distribute exponents over addition, because we know that that doesn't work with the second power. We can't say that's x squared plus y squared. And it's not going to work for the third either. X plus y all cubed is not going to be x cubed plus y cubed. So what is it? Well, one way we could do this is to use the rules for exponents and say, well, this is x plus y all squared times x plus y. Right? Something to the third power is that thing to the second power times itself. And then use the fact that this then is the previous power that we had. So that's x squared plus 2xy plus y squared. and then multiply that by x plus y. And now we have to FOIL all of this out yet again. So let's see what we get here. Now, FOIL, I'm using this more than just first, outer, inner, last. I'm using it to distribute any two polynomials, expand any two polynomials in their product. So if I distribute the x squared across, I get x cubed plus x squared y. Distribute 2xy across x. X squared y across y, 2xy squared. And then distribute y squared across. Xy squared plus y cubed. And now I can collect like terms. There's an x squared y, a 2x squared y, 2xy squared, xy squared. So altogether, I see that I get x cubed plus 3x squared y plus 3xy squared plus y cubed. Okay, so let's stop and just keep track of this. So even right now, you might want to make some observations. Pause the video and see if you notice, if you're not familiar with the binomial theorem, see if you notice any patterns here. So this is how math is done. You try and find patterns, and you try and make conjectures or guesses about what something would be, and then you see if it's true. You try and prove it or disprove it. Let's go on to the next power. Now for x plus y to the fourth, there's a couple ways we could go here. We could do the previous power, the cube, and then multiply it again by x plus y, like we did to getting the cube from the square. We could also just square x plus y squared. Now, they should give us the same thing. Let's do it with x plus y squared squared. So x squared plus 2xy plus y squared times x squared plus 2xy plus y squared. Okay? What is that going to give us? So again, we have to FOIL everything out. So we're going to distribute the x squared across, the 2xy across, and the y squared across. So let's multiply out. Distribute the x squared. We get x to the fourth plus 2x cubed y plus x squared y squared. Okay, now we're going to distribute the 2xy across. 2x squared y, another 2x squared y, a 4x squared y squared. Sorry, this was 2x cubed y. Sorry, this should not be x squared y. We're distributing 2xy across x cubed, so it's x cubed y. Okay. Then the 2xy multiplied by itself, right, gives us 4x squared y squared. 2xy times y squared is 2xy cubed. Now we distribute the y squared across, get another x squared y squared, 2xy cubed, and y to the fourth. And again, now you can see why you don't want to do this too much, right? This is getting pretty lengthy. So we went to collect like terms. So let's see, there's x cubed y, x cubed y. There's x squared y squared, x squared y squareds. And then there's xy cubed, xy cubed. And now if we combine all these, we get x to the fourth plus, collecting the blue terms, 4x cubed y plus, collecting all the green x squared y squareds, makes 6x squared y squared, plus the reds is another 4xy cubed, and then plus y to the fourth. Okay. Now, what I've done here, you may have noticed, is I've written these in a certain way. So I've written the terms in a certain order. I've arranged the x's and y's in a certain way because I know how this is set up. But let's go back, and so we have the fourth power, the third power, the squared power. Let's go backwards and see, well, what would it mean if we went backwards? What's the first power or the zero power? So let's collect these together. So I'm going to rewrite here, x plus y to the 0, which would be 1, because anything to the 0 is 1. X plus y to the first, which is x plus y. And then we could bring these other ones and let me copy them and bring them down. Okay, so what I want you to do is pause the video right now, and what I want you to do is just make a list of patterns that you see. So there's things that seem to be, because you got 5 expressions here, so that should be enough to try and guess any patterns that you see. The things that you notice about the way it's written, about the pattern of the x's and y's, about the coefficients maybe, and just make a list, as many observations as you can. I'll come back in a minute and we'll go over what you got. Okay, so hopefully there's a few things you should have come up with. So first of all, let's add some stuff here. This is going to be helpful if I write the powers 1. So on all these, if I actually write the power 1, and also if on this one I write x to the 0, y to the 0, and if I secretly imagine that on the ones where it's just a like x squared, x cubed, x to the fourth, if I remember that I really could make this, I'm going to write this a little bit different, x to the first, y to the 0, plus x to the 0, y to the first. And the same thing here. And also, I could put, if there's no coefficient, it's really coefficient 1. So we've got 1, x to the 0, y to the 0. I could really write the second one as 1, x to the first, y to the 0, plus 1, x to the 0, y to the first. I could write this as 1, x squared, y to the 0, plus 2, x to the first, y to the first, plus 1, x to the 0, y squared. And the same thing here, I could put, well, let me do y to the 0, 1, x to the 0, so plus 1, x to the 0, y cubed, 1, x to the fourth, y to the 0, x to the 0, again. Yeah, there we go. I could write this as just plus 1, x to the 0, y to the fourth. Okay, let me clean this up just a bit. Okay, so I think this is the form that I'm looking at. So writing it this way, what do you notice? Well, you notice every term I've written with powers of x and y. And then notice that within a particular expansion, notice these two, 0 plus 0 is 0. Notice that these always equal 1, which is the power here. 2 plus 0, 1 plus 1, 0 plus 2, those all equal 2. So do you see what's, oh, I left off of 1 here. 2, 1, 2. So what you notice is, one thing is, for each term in the expansion, you get the powers of x and y are adding up to the power in the binomial, the power that the binomial is raised to. So for instance, when you do x plus y all cubed, you get a bunch of terms with x and y powers, and the powers on the x and y are always going to add up to 3 because that's the power. Okay. So that means we could arrange them where all the powers are starting with x, and then you decrease the powers of x by 1, you increase the powers of y by 1 until they're all y. And that's what I've done here. Right, I've started with the biggest x power, and then they just transfer over to y until you get the biggest y power. Well, now let's look at the coefficients. That's really the thing that's left over to think about. What are the coefficients? Here it's 1. Here the coefficients are 1 and 1. Here they're 1, 2, 1. Here they're 1, 3, 3, 1. 1, 4, 6, 4, 1. Interesting. Now, this may remind you of something. Even if you haven't seen the binomial theorem, you may have seen this before. One, 1, 1. 1, 2, 1. 1, 3, 3, 1. So what's going on here? I started with 1. And then each additional row, you get the number by taking the sum of the two above it to the left and right. So you have 1s on the outside, and then the ones in the middle you get by going up to the left and up to the right, and you add those two. So 1 plus 2 is 3. 2 plus 1 is 3. So what's this one going to be? We start off with 1s on the outside. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And notice that's exactly 1, 4, 6, 4, 1. That's funny. Should be something that really strikes you. What on earth does something that has to do with algebra, purely algebraic thing, multiplying out a power of a binomial and collecting like terms, what does that have to do with this funny triangle I've given with this rule about how you get, the next number by doing some adding? Seems like these are not related necessarily, but it turns out they are. So whenever you see something where it's really striking, something from over here and something from over here that seems like they're not related, and you see that they're really the same, you need to ask, well, what's really going on here? Let's keep going. 1, 5, 10, 10, 5, 1. So we can make a conjecture now. And I'll let you pause the video and multiply it out to check. What should x plus y to the 5th be? If this really is holding up, if this is our guess about what's going on, we should get x to the 5th, right? Because you start with all the powers in the x. You decrease x power and increase y. So plus, then these are the coefficients, right? So now the coefficients are 1, 5, 10, 10, 5, 1. So it'd be 5 x to the 4th y plus 10 x cubed y squared. So decrease x, increase y, still add up to 5, plus 10 x squared y cubed plus 5 xy to the 4th plus y to the 5th. Okay, it should be all of that. And what I'll do is I'll go ahead and let you pause the video, go back up and figure x plus y to the 5th. You can take the 4th power and multiply by x plus y, or you could multiply x plus y squared and x plus y cubed together, whichever you want to do. It's up to you. Just check that that's what you get. Okay, so come on back. Okay, so hopefully you're able to check that now. Now, when you make a conjecture like that and you guessed what it was and it turned out to be right based on that, now this is really, it's not a proof of anything, but it's strong evidence that we're on to something here. This is probably right. 15, 20, 15, 6, 1. And so this pattern of these numbers that are emanating from the top row here. This is what you may have seen before. This is something called Pascal's triangle, named after Pascal, although like many things in math, he wasn't really the first to come up with it. This was known hundreds and hundreds of years before him. It's just a lot of things in math are named after the first European that is associated with them, and so that's him. But this was, I believe it was known in China for a long time before Pascal. So what is the connection going on here? So these numbers here, there's a name for these. These numbers are called binomial coefficients. Now, why are they called binomial coefficients? Well, because they are the coefficients that come when you take a binomial raised to a positive integer power. It's a very straightforward name. But what we're going to see is these binomial coefficients are much more than just algebra. They have a counting interpretation that's very important. So that's what I want to, that's what I want to lead you through right now, is what's really going on here? There's something kind of mysterious going on here. And so we're going to take a step back and talk about some other things for a moment. And then we'll come back and we'll see why we get these numbers. So let's start off with counting. And I'm going to kind of go through some of this quick. I'll give some videos where they go over some more of this. But we'll start with, when I say counting, I don't mean 1, 2, 3, that kind of counting. I mean, how do you account for the number of things that have a certain property? So there's a number of different principles. The main ones is the multiplication principle. And what it says is, if you have a series of tasks that you want to do, and each task can be done a certain number of ways, and the decisions you make on one task do not affect the future task decisions, then the total number of ways of doing everything together is the product of the number of ways of doing all the tasks. Now, that sounds very verbose, so let me go through an example. Suppose you're at a meal, and there's 3 appetizers, 4 main courses, and 2 desserts. And let's say that you have complete freedom over what you want to order. So, if you have steak, you're allowed to have either of the 2 desserts. It's not, if you have calamari, you can have whatever else after that. It doesn't matter. How many meals are there? Well, multiplication principle says that's 3 times 4 times 2. So in this case, 24 possible meals. Now, why does this work? Something called a tree diagram. You could look at the appetizers and say, there's 1, 2, 3 possible appetizers. Once I've selected one of those 3 appetizers, I could go into 4 meals. Okay, and you can see already here I've got, say the meals are 1 through 4. So you can see I already have 4 plus 4 plus 4. I already have 12, which is 3 times 4. So just the appetizers and the meals, I multiply to get 3 times 4, which is 12. And then you get the desserts, and now you have to take into account that each of these is going to split up. All right. Okay. So then you get times 2. These are the meal, main course, and then the dessert. So 3 times 4 times 2, and that's where you get the 24. So notice that what has to happen here. It has to be a series of tasks, sequence of tasks. The number of ways that you do it always has to be the same no matter what you've done before. So the first task can always be done 3 ways. You always have 3 appetizers to choose from. The main course, you always have 4 ways to choose that. Doesn't have to be the same choices, has to be the same number of choices. That's kind of a subtle point that if this was a different class, I'd go into more, but the same number of ways. So you always have 2 desserts. Okay. So 3 times 4 times 2 is 24. Why is this important? Well, this is going to lead into permutations and combinations. So let's talk about that. So what is a permutation? A permutation is an ordered selection of objects. Okay, so let's say you have 5 letters, A, B, C, D, E. How many ways to select 2 from these 5 in order? Well, we could list them all. Okay, we could select A first, and then after that, we could select B, C, D, or E. We could select B first, and then do A, C, D, or E. We could do C first, and so on. So you see the kind of pattern here. Or we could do D first, and then A, or B, or C, or E, or E. Okay, so what's going on here? So we don't want to, point is we want to know how many of these are there without writing them all out every time. So here there's 20. Notice that's 5 columns times 4 rows. Okay. Why does this work? It's the multiplication principle. Think of filling in 2 blanks. There's 2 tasks. The first task is how do you fill in the first blank? The second task is how do you fill in the second one? How many ways to get the first letter? Well, at the beginning, you have, so I should say these are selections without replacement. So once you select something, you can't select it again. You can't put it back into the collection. Okay, that would be a different problem. How many ways can you choose the first letter? Well, there's A, B, C, D, or E. So there's 5 possibilities. And then how many ways to choose the second letter? Now, you may have different choices. Depending upon which letter, there's going to be 4 different letters left. So it might not be the same 4 letters, but there's always 4 of them remaining because you took out 1. So how many ways for the second letter, for getting the second letter? It's 4. So you have 2 tasks. The first one can always be done 5 ways. The second one can always be done 4 ways. So the multiplication principle says altogether 20 ways. Okay, so you can see kind of, so what we would hear is we would say that this is, the notation would be 5, 2, and we would say this is 5 permute 2. So 5 permute 2 is equal to 20. Okay, let's go through some other examples. Okay, how many 7-letter license plates if no letter can be repeated? Okay, so this is equivalent to the problem of a permutation of 7 out of 26 letters in the alphabet. So this would be 26 permute 7. And now notice, however many you're permuting, so however many you're selecting, that's how many factors. So the way to think about this is you start off at 26, 25, 24, 23, 2, 21, 20. 1, 2, 3, 4, 5, 6, 7. Okay. And then you would multiply all of these up. Now, what does this turn out to be? So this is 3,315,312,000. Pretty big number. So you can see these numbers get kind of big. Now, if I wanted to write a formula for this P with number, if let's say that I'm selecting k objects out of n. So I want a formula for P n k, which would be n permute k. So this is going to be the number of ways of selecting k objects out of n. The formula for this turns out to be n factorial over n minus k factorial. Now you have to know what factorial means. So here factorial is the product of the numbers n, n minus 1, n minus 2, so all the way down to 1. Or you can think of it as starting at 1 and going all the way up to n. And 1 factorial equals 0 factorial. Those also equal 1. Now, why does this work? Let's look at 26, 7. This would be 26 factorial over 26 minus 7 factorial, which would be 19 factorial. So what that's saying is take all the numbers from 26 all the way down to 1, and then divide by the product of all numbers from 19 all the way down to 1. And what you see is there's canceling. Right? The 19 cancels with everything down to 1. So all that you're left with is this stuff. You're just left with 26 to 20. So this is a formula that works right here. Okay, so this is permutations. I want to select with order. There's a first thing, second thing, third thing, fourth thing. What if I wanted to do the same thing without replacement, but unordered? So instead of order, it's unordered. So what that would mean would be, when I'm looking over here, BC and CB, these would really be considered to be the same. If it was a so we're going to call these combinations. So a permutation, the order matters. So permutation, BC is not the same as CB. But with a combination, they are the same because it's just, it's B and C. It doesn't matter what order. So that's called a combination. It's an unordered selection of objects. This is a lot of stuff that you would go through in a statistics class if you study probability theory, or in a discrete math or finite math class where you'd study counting and probability. Okay, so combinations. So as we ask for permutations, these are an unordered selection of objects without replacement. So we could ask the same question we did above. How many ways of, so the way that you kind of say this in math is choosing. How many ways are there of choosing 2 objects out of 5? Okay, so in this case, again, we have A, B, C, D, E. But now, when we're listing how many combinations are, there's just AB, AC, AD, AE. Now, when we start with B, though, we don't list BA like we did before, right? So up here we listed BA as separate, but BA is the same as AB because it's just A and B. It doesn't matter the order. So now we can go BC, BD, BE, but then we could include C, but we've already got C and A, C and B. So the only other real thing is C and D, and then C and E. And you should be able to see there's only one more left, DE. Now, how many is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we would say that C for combination. So we read this as 10 choose 2 is, 5 choose 2. Sorry about that. 5 choose 2 is equal to 10. Okay. Now, how could we figure this out? Because we don't want to just list these all the time. Well, there's a way that we could figure out a formula for this. By the way, another notation for this is 5, 2. So it's written like a fraction in parentheses, but there's no fraction bar. It's called 5 choose 2. Okay. Question, is there a general formula? Just like we found for permutation, is there a general formula for N choose K or this? And the answer turns out to be yes. So how do we figure this out? Well, by multiplication principle, there are 2 ways to make an ordered selection of K objects out of N. But there's 2 ways to count the number of, I should say there's 2 ways to count them. There's only one way to do it, but there's 2 ways to count the number of ordered selection of K objects out of N. So what are these 2 ways? Number 1, by definition, the number of ways to do this is N permute K, right? That's what an ordered, it wasn't unordered, ordered. But there's another way to do it. We could break this down into 2 tasks. First, make an unordered selection. In other words, just say what's going to be in the selection at all. And don't worry about what order they come in. And then second, so this is first, and then second, order the ones that you picked. Okay, so you got the difference? The first way, you just make the unordered selection as the first. Okay, I'm going to take the first, the second, the third, and so on. Let's say you're taking 10 objects. I'm going to take the first, second, the third, fourth, fifth, sixth, seventh, eighth, ninth, all the way up to the 10th. The second way of doing it is to say, okay, I'm just going to reach in, mix them up. I'm just going to grab 10 of them. I just take 10 objects out. And then I'm going to order them. So then I lay the 10 objects out in front of me. And I say, okay, I have to order these. Okay, here's the first, the second, the third, the fourth. And I put them in an order. Okay. How many ways are there of doing it by this accounting? Well, how many ways can we make the unordered selection? Well, and here, I need to move this to the left a bit. So to make an unordered selection, by definition, this is N choose K. N choose K ways to do that. Then how many ways can I order those objects? Well, this is K permute K. So that means by multiplication, there's going to be N choose K times K permute K ways of doing it all together. So since I'm counting the same thing, these two must be equal. In other words, the number of permutations of k objects out of n has to be equal to the number of combinations times the number of permutations of k objects out of k objects. But how many ways are there to permute k objects out of k objects? Well, let's see. If we look at the formula, this would be k factorial over k minus k factorial. Now, 0 factorial is 1, so this just ends up being 1, so we just get k factorial. Another way to think of it is, if you're rearranging k objects, the number of ways of doing it is k minus 1, k minus 2, all the way down to 1. So if you're rearranging, say, 10 objects, it's 10 times 9 times 8 times 7, 6, 5, 4, 3, 2, all the way down to 1. So that's 10 factorial. In this case, k factorial. So another way to write this equation is, number of permutations is n choose k times k factorial. But we've already seen that the n permute k, we already have a formula for that. So we saw that we could write that as n factorial over n minus k factorial. So now if we solve this equation for n choose k, we can do that by dividing everything through by k factorial. Divide by k factorial, divide by k factorial. And so we end up with this really nice formula that I'll summarize over here. So n choose k is equal to n factorial all over n minus k factorial times k factorial. Okay, so that's the formula. Now, that's not really what you're going to use in practice. So what I'm going to do is show you what this formula looks like for a particular value of n, and show you an easier way to think about this as far as computing specific binomial coefficients. So first, let's look at an example. Let's look at n equals 5. So for n equals 5, we could look at, now, how many things can you choose out of 5? Well, you can either choose 0, 1, 2, 3, 4, 5. You can't choose less than 0, you can't choose more than 5. So there are 6 binomial coefficients here. 5 choose 0. 5 choose 1. 5 choose 2. Actually, let me, just a second. 5 choose 2. 5 choose 3. 5 choose 4. And finally, 5 choose 5. Okay, and I'll move all of this over to the left just a bit. Okay, so let's see what these are. 5 choose 0. So I'm just going to plug into the formula. 5 choose 0. So this would be 5 factorial over 5 minus 0 factorial. So that's 5 factorial, 0 factorial. Notice that the two factorials, the two numbers you're taking the factorials of in the denominator always add up to n. So they're always going to add up to the upper number. So 5 here. So it's going to be 5 and 0. 5 plus 0 is 5. Now, 1 factorial reduces to 0 factorial reduces to 1. And then 5 factorial over 5 factorial, well, it doesn't matter what 5 factorial is. Those are going to cancel. So this is going to be 1. So 5 choose 0 is equal to 1. Now, think about this in terms of counting. What this is saying is, how, if you have a bag with 5 marbles in it, how many ways can you choose none of the marbles? There's one way. Now, you might think there's no ways of doing it because you're not choosing anything, but actually there is one way. I hand you the bag of marbles. You take it in your hand. You stare at it for a few seconds in contemplation, and then you hand it back to me. Okay, so you're doing something. You're doing the something of nothing. You're not doing anything, but there's one way to do nothing. So that means 5 choose 0 is equal to 1. Now, what about 5 choose 1? What should this be? Well, there's going to be 5 ways to do it. Right? You choose the first, second, third, fourth, or fifth marble. And the formula confirms this because it's 5 factorial over 5 minus 1, 4 factorial, 1 factorial. 1 factorial is defined to be 1. So this is 5, just 5. And that's the way that we said about the permutation would be 5 just one factor, but we're dividing by 1 factorial. So it's really 5, 4, 3, 2, 1 over 4, 3, 2, 1. And then these end up canceling. So 5 choose 1 is equal to 5. What about 5 choose 2? Well, this would be 5 factorial over 5 minus 2 factorial, so 3 factorial, 2 factorial. So notice the pattern here. 5, 0, 4, 1, now 3, 2. And this is 5, 4, 3, 2, 1 over 3, 2, 1 times 2, 1. Okay, 3, 2, 1 goes out. Now 5, 4, 2, 1, 2. 5 times 2 then is 10. So this is 10. Okay, now I claim that we've calculated everything we need to calculate because 5 choose 3, this is really going to be 5 factorial over 5 minus 3 factorial, which would be 2 factorial times 3 factorial, which is really just the same as this, right? 2 factorial times 3 factorial is the same as 3 factorial times 2 factorial. So 5 choose 3 is the same as 5 choose 2. 5 choose 4 is going to be 5 factorial over 1 factorial, 4 factorial. So it ends up being the same thing as this, which turned out to be 5. 5 choose 5, 5 factorial over 0 factorial, 5 factorial. So this ends up being, so you see there's a symmetry to the numbers here. Now, do these numbers look familiar? 1, 5, 10, 10, 5, 1. They should look familiar to you. If you go back up to Pascal's triangle, we're doing all the way back up here. Look at 1, 5, 10, 10, 5, 1. That was the fifth row, or the sixth row, depending on how you count it, but the fifth row of Pascal's triangle, 1, 5, 10, 10, 5, 1. And those were the coefficients that we got when we expanded x plus y to the fifth. So what on earth is going on here? How do these coefficients over here, given by this triangle pattern, also answer this counting question about how many ways you can select, make a selection of objects out of something else? Still very mysterious what's going on here. So let me try and give you the best explanation for why this works the way it does. So let's look at x plus y to the fifth. What are we really doing when we're taking x plus y to the fifth? Well, we're multiplying x plus y, 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 right? We're multiplying it out 5 times. Now, when you multiply out a bunch of polynomials times each other, how many terms do you get? In general, you get, the terms that you get are the sum of all the products whose factors are a factor from each individual binomial. So let me say that again. If you think about distributing across, when you're distributing it across, you're really getting all the possible patterns of one factor with another. So xx, xy, yx, yy, right? That's like foiling. If there's more than one factor, you just continue the pattern. It's like the multiplication principle. You have 2 choices of terms from the first factor, 2 choices from the second, 2 choices from the third, and so on. So let's see. What this amounts to then is, first of all, you notice that all the terms, because of this fact, will be of degree 5. Now, remember, for polynomials of 2 variables, the degree is the sum. So you're always going to get the sum. You're going to get so many x's and so many y's, but together they have to add up to 5. So in other words, they're either going to be x to the 5th, or x to the 4th y, or x cubed y squared. So 5 x's, 4 x's, 3 x's, 2 x's, 1 x, or they're all y's. How many of this, say, do we have? Let's just go through this as an example. So how many of these, now we can even say how many there are, because there's, by multiplication, there's going to be 2 times 2 times 2 times 2 times 2. How many of these 2 to the 5th equals 32 terms? And they all have coefficient 1 right here, because it's 1x plus 1y. How many of these 32 terms are of the form x cubed y squared? How many of these are of the form x cubed y squared? Well, what that amounts to is, if you think of the 5 factors, the 5 binomials getting multiplied together as 5 blanks. And what we're being asked to do is list x's and y's here, like the license plate. Remember the license plate problem where we said we're kind of filling things in, except here we're filling in x's and y's, and we could have repeats. But the difference is we're going to list x's and y's here so that we get, so there are 3 x's and 2 y's. So for instance, I could do x, 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 y, y. So this would be saying I get an x cubed y squared term if I selected x, y, x, x, y. Okay, that's one possible pattern. When I FOIL this out, I could take x from there, y, then x, then x, then y. And that particular term would have coefficient 1, and it would generate an x cubed y squared. So how many of those are there? Well, how many ways, this is then asking, how many ways are there to select 3? Well, actually, let's see now. Let's think instead about actually placing the y's to select the 2 y's. In other words, where the 2 y's go. So out of the 5 places, I have to select 2. This one and this one. So it's like saying out of A, B, C, D, E, this would be B and E. Or out of 1, 2, 3, 4, 5, be the 2nd and the 5th. So I'm making an unordered selection where the y's go. I make an unordered selection of 2 out of 5. That's how many terms are x cubed y squared. How many ways can I make an unordered selection of 2 out of 5? Well, we just answered that. It's 5, choose 2. And there's your answer why that's the coefficient. 5, choose 2, which is equal to 5 times 4 over 2 times 1, which is 10. So that's why we get a 10. Now, there's a lot we could say about these numbers. What I'm going to do now is state exactly what the binomial theorem says, and then we're going to practice computing some binomial coefficients and just answering some basic questions about expansions. So just the algebraic applications. Okay, so let's look at a couple quick examples. Let's look at 9, choose 4. So let's see, how do we evaluate 9, choose 4? So the way that you actually evaluate these in practice for specific small numbers like this is you don't actually write out the formula and say, okay, it's 9 factorial over this factorial, this factorial. You follow the pattern. So you start with a number on top. Okay, so we're going to go 9, 8. And what you're going to do is make a permutation with the number of elements on the bottom. 9, 8, 7, 6. Okay, there's 1, 2, 3, 4 factors. Then you have to divide by that factorial on the bottom. So it's 9876 divided by 4, 3, 2, 1. This will always divide evenly. So in this case, there's going to be some canceling. 6 and 6 cancel. 4 goes into 8 twice. And so we end up with 9 times 2 times 7, which is going to be 63 times 2, so 126. So 9 choose 4 is 126. Do a couple more examples. 40 choose 3. 40 choose 3. 40, 39, 38 over 3, 2, 1. So you see the pattern? That number, you fall down, that many on top, 40, 39, 38. Okay, I've got the 3 numbers on top. Then you divide by that factorial on the bottom, 3, 2, 1. Remember, the numerator is the number of permutations. And then the denominator is taking you to a fact that you have to divide by the number of ways of rearranging the things amongst themselves. Again, there's canceling here. Okay, so that's 13, 20. So it's 20 times 13 times 20 times 13 times 38, whatever that turns out to be. Okay, what about 73 choose 0? Now, this is leading to one of the main properties of binomial coefficients, which is that anything choose 0 is always 1. Because how many ways can you choose nothing out of some things? There's only one way to do it. Another way is if you look at the formula. So if you look at the formula, you see that n choose 0 is always going to be n factorial over n factorial 0 factorial. And notice that's also going to be n choose n. So n choose n, this is like saying if you have 13 marbles in a bag, how many ways can you take all 13? Well, there's only one way to do it. You just take them all. That's it. There's no other way to take all of them. So 73 choose 0 is 1. And this is because 0 factorial is 1. This is 1. And then, of course, those cancel, leaving 1. So 73 choose 0 is 1. But also something like 81 choose 81 is also 1. Now, what if I asked you this? What if I said, what is 100 choose 98? Now it seems like this is going to be really tricky because you have to count down 98 numbers, 100, 99, 98, 97, right? And then divide by 98, 97. But if you remember that symmetry we talked about in Pascal's triangle. Pascal's triangle reads the same left to right as right to left, any row. And the way that we can express this is a little identity. And the way we would say that is we have this identity that n choose k is equal to n choose n minus k. Why? Because each of these is equal to n factorial over n minus k factorial k factorial. Okay, so the way it's written here is the definition of n choose k, but if you apply that to n minus k, what's n minus an n minus k? N minus n plus k would be k factorial, and then you have the n minus k. So the factors would just switch. So although 100 choose 98 would be 100 factorial over 2 factorial 98 factorial. That is the same as 100 factorial over 98 factorial 2 factorial, which would be 100 choose 2. And 100 choose 2 is much easier to do because that's just 100 times 99 over 2 times 1. And so you can just take that. Okay, that's 50. So it ends up just being half of 9,900. So that's 4,950. Okay, so that's another thing to be aware of with these binomial coefficients. So we've got, the choose 0, the choose n, the n choose k, essentially n minus k, and also anything choose 1. So like 314 choose 1 is going to be 314. So n choose 1 is always equal to n because you have 314 over 1. There's 314 objects. There's 314 ways you could select one of them. Okay, so this is kind of the practical way that you actually compute these coefficients. Now, let me give you the statement of the binomial theorem. Binomial theorem then says that x plus y raised to the nth power, this is for n, bigger than or equal to 2, although I guess it works for 1 as well, or 0. This is, okay, so we're going to start with the biggest x power, which would be n to the 0. So it's n to the 0, x to the n, y to the 0, plus n choose 0, n choose 0, x to the n, y to the 0, plus n choose 1, x to the n minus 1, y to the first, plus n choose 2, x to the n minus 2, y squared. See the pattern? All the way down to the last, let's give the last two terms. The last two terms would be n, choose n minus 1, x to the first, y to the n minus 1, and then plus n, choose n, x to the 0, y to the n. Now notice the pattern to all these terms. In fact, let me clean this up so that one extra term there at the end is bugging me. Much better. Okay, so if we write this in summation notation, so if you've seen sigma notation before, and if you haven't seen it, don't worry about it too much, but in sigma notation, this would be x plus y all to the n is equal to the sum from k equals 0 up to n of n choose k, x to the n minus k, y to the k. Now, this form of doing it it's a very abstract kind of algebraic form. In practice, usually if it's with a specific number, you want to think of the binomial coefficients, and if it's small enough, you want to think of the rows of Pascal's triangle. Right? So if you're raising something to the 5th power, you don't think in terms of, this formula that you're plugging in, you think in terms of, the coefficients are, if I draw the triangle down to 5, the coefficients are 1, 5, 10, 10, 5, 1. Or if it's down to 4, it's 1, 4, 6, 4, 1. Okay, so we need some practice. So let's look at just one example. Let's look at, let's make it 3y. So let's start with x plus 3y all to the 4th. Okay, so what you want to do here is think of Pascal's triangle, think of the binomial coefficients. 3, 1, 1, 4, 6, 4, 1. Okay, so we got 1, 4, 6, 4, 1. So we start with x to the 4th plus, and we move along. Okay, now we're at 4. So we pick up a coefficient of 4. But now, you have to remember here that this is like the first. It's like first plus last, except it's not just x and y, it's x and 3y. So we have to think of the 3y in parentheses when we multiply this out. So it's x to the 4th plus 4 x cubed 3y plus 6 x squared 3y all squared plus 4 x 3y cubed plus 3y all to the 4th. So look at the pattern here. You've got the coefficients 1, 4, 6, 4, 1. You got x to the 4th, reducing in power x to the 4th, x cubed, x squared, x to the 1st, and then no x. And then you've got the increasing powers of 3y. And of course, we should kind of multiply stuff out here, and we get x to the fourth plus 12x cubed y plus, we've got a 9 and 6, it's 3 squared and 6 would be 54 x squared y squared plus 27 times 4. What is 27 times 4? 108. So plus 108 xy cubed, and then plus 81 y to the fourth. Okay, so if you look at that, think about how much time that would have taken to multiply out completely. It would have taken quite a long time. So this is a really nice result here. Let's look at one more example. We're going to multiply something out. So let's do p squared minus q all to the 6th power. Okay, so we need to have another couple rows here. 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. Now you may be wondering, well, what if it's to a really high power? Well, then you just have to compute the binomial coefficients somehow. If it's like 20 or 31, you don't want to go all the way down like that. Now, one thing to notice here, we have a minus sign. What that's going to do is have the effect of alternating the signs. Now, the reason for this is we can write this as minus q. So subtracting q is the same as adding minus q. So this is going to be p squared to the 6th plus 6 p squared to the 5th minus q to the 1st plus 15 p squared to the 4th minus q squared. And now you see that the reason we get the plus minus pattern is that term with the minus sign, when you alternate even and odd powers, it changes from plus minus to minus plus. So the minus q squared is positive, but the minus q cubed then is going to be negative again. So then we've got a 20 p squared cubed minus q cubed plus another 15 p squared squared minus q to the 4th plus 6 p squared to the 1st minus q to the 5th, and then finally plus minus q to the 6th. And if we multiply that all out, so we get p to the 12th minus 6 p to the 10th q plus 15 p to the 8th q squared minus 20 p to the 6th q cubed plus 15 p to the 4th q to the 4th minus 6 p squared q to the 5th plus q to the 6th. It's a lot. Okay. Notice the alternating pattern. The signs start off positive, negative, positive, negative. So plus, minus, plus, minus, plus, minus, plus. That'll always happen when it's a difference, when it's something subtracts something. Okay, couple last quick problems to finish up here. On a couple of the problems, they ask you to find like the first 3 terms, or maybe find a very specific term in a binomial expansion. So let's look at a couple of those. So let's find the first 3 terms in the expansion of x plus 2y to the 26th. Now, obviously here you don't want to write out the entire expansion. At the same time, you don't want to use Pascal's triangle to figure out the binomial coefficients. So we're going to use the actual formula here. We know that x plus 2y to the 26th And now I'm going to write it out just like I would before, except I'm going to write it in terms of the binomial coefficients, and I'm not going to write all the terms. So we know the first term is going to be x to the 26th plus 26 choose 1, x to the 25th, 2y, plus 26 choose 2, x to the 24th, 2y all squared, plus dot, dot, dot. And since we only want the first three terms, doesn't matter what the rest is. So I'm just going to put dot, dot, dot. And now we can at least multiply these out. So x to the 26th. We know that 26 choose 1 has to be 26. And 26 choose 2, let's just do this on the side. We know that's 26 times 25 over 2. 25 times 13, which is going to be 325. So we'll get 26 times 2, 52, x to the 25th y, plus, so this was 325. And then we have another factor of 4, because it's 2 squared. So 1300 x to the 24 y squared plus dot, dot, dot. Okay, so those are the first three terms of the expansion. Okay, the last example I'll do, they're going to ask for a term with specific powers of the variables. And you have to be careful. If you notice on this one, because it was p squared here, not all the terms had the same degree. This is degree 12, degree 11, 10, 9, 8, 7, 6. That's because although the degrees are the same in the binomial theorem, if one of them is a power of a variable, then it's going to change the degree of the terms in terms of that variable. So last example, find the term containing x to the 7th in 2x minus y all to the 10th. So we only need a specific term here. So what is this term going to look like? So the general term of 2x minus y to the 10th is, so it's going to be 10 choose k times 2x to the k, to the 10 minus k, times minus y to the k. So in other words, if we're going to get x to the 7th, this power here has to be 7. So the 2x has to be raised to the 7th power. The minus y has to be raised to the 3rd power. So it's going to be 10 choose 3. So we have 2x to the 7th minus y cubed. Okay, so we got the two terms. One of them's to the 7th, the other one's cubed. 10 choose 3. Notice if you got mixed up and do 10 choose 7, it's the same thing, so it doesn't matter. Okay, and what does this give us? Well, 10 choose 3 is 10, 9, 8 over 3, 2, 1. That's 120. So it's 120 times 2 to the 7th times x to the 7th minus y cubed. Okay, what's 2 to the 7th? 2 to the 7th is 128. Okay, and then 120 times 128. What is 120 times 128? So, there's no shame in using a calculator here. 15,360. Okay, so we would get 15,360. There's also a minus sign, so minus that. X to the 7th, y cubed. So minus 15,360, x to the 7th, y cubed would be the term in the expansion of 2x minus y all to the 10th that has a power x to the 7th. Okay, this is a lot. If you've never seen the binomial theorem or anything to do with counting or permutations and combinations, this can be a lot. But this is a very, very useful result when you're doing expansions of things and when you're doing a lot of algebraic computations. It really helps out a lot. So even though it doesn't seem like it's something we're going to use a whole lot, I would really encourage you to watch the video through again and really try the problems and really try and understand it. Okay.